Hello, my name is Samira Nasrin, and today let's study about reactions of haloalkenes. The reactions of haloalkenes may be divided into the following categories. There are three categories given. First one is nucleophilic substitution reaction. Second one is elimination reactions, and third one is reaction with metals. In this particular session, we are going to be studying about nucleophilic substitution reaction in detail. Okay, so nucleophile, what is a nucleophile? Nucleo is something related to nucleus. We know that nucleus is positively charged and phile means loving. So the nucleophile is a species that has affinity towards the positive charge. That is obviously electron-rich species. This nucleophile will attack the electron-deficient part of the substrate, and the substrate being our alkyl halide. The reaction in which a nucleophile replaces already existing nucleophile in a molecule is called nucleophilic substitution reaction. So here a general reaction is given. This is our substrate alkyl halide. The halogen being more electronegative than carbon, this bond will become a polar bond, and the halogen atom will have a partial negative charge and the carbon atom will have a partial positive charge, which means this carbon is the electron deficient part of the substrate. So our incoming nucleophile will attack this electron deficient carbon, and subsequently the halide ion will leave the product and we'll get a product in which the halogen atom is replaced by a nucleophile. So according to the reagent that we take, we can prepare a wide variety of products by this reaction. So this is a very useful reaction. For example, if you are taking NaOH, we'll get a nucleophile OH minus, and we'll end up with alcohol as product. If you are taking H2O, the nucleophile is H2O itself, and we are again getting an alcohol. So here, one point to note is that when we are taking NaOH, the nucleophile OH minus is a negatively charged species, and H2O here it is a neutral species. A neutral species is acting as a nucleophile, so it is not necessary that a negative charge should be there in the nucleophile. A neutral species can act as a nucleophile as well. Here, the oxygen atom has got two lone pairs on it. Two lone pairs are there, and that is why the water molecule is acting as a nucleophile. These are all similar examples, and here ammonia as well. There is a lone pair of electron on the nitrogen, and we are getting a primary amine as product. One of the interesting cases in this table is of KCN and AgCN. They both may look similar to each other, but the product that we are getting when we take KCN and AgCN are different. If you are taking KCN as a reagent, the product that we are getting is a nitrile. If you are taking AgCN as a reagent, what we are getting is isonitrile. It is because KCN is an ionic product where there is a positive charge. K is a positive charged ion and Cn is a negative charged ion. So the new bond is formed between this carbon and the electron deficient carbon of the substrate, and we will end up with a cyanide. When we take AgCN is a covalent bond, so the attack is happening, the new bond is getting formed through this nitrogen, and we will end up with the isonitrile or isocyanide. A similar case is also can be seen here as well. When we use KNO2, we will be getting a alkyl nitrite, and if we are using AgNO3, we will end up with a nitroalkane. So these kind of nucleophiles, where the groups like cyanide and nitrides possess two nucleophilic centers and are called ambident nucleophiles. So, uh, if you are taking cyanide, for example, okay, if you are taking this group as an example, this particular nucleophile can form bond with using this carbon or this nitrogen. So this sort of nucleophiles, another example being NO2. This can form a bond using this nitrogen or using one of the oxygen. So these sort of nucleophiles are called ambident nucleophiles. Now let's see the mechanism of substitution, nucleophilic substitution reactions. There are mainly two type of mechanisms that can happen. First one is substitution nucleophilic bimolecular reaction, which in short is called SN2 mechanism. Then the second one is substitution nucleophilic unimolecular mechanism, which is which is in short called SN1 reaction. Let's see substitution nucleophilic bimolecular reaction in detail. So, as the name itself suggests, substitution nucleophilic bimolecular reaction is a bimolecular. Uh, it's a bimolecular reaction, which means the rate of this reaction, if the reaction is proceeding by using this mechanism, the rate of this reaction will depend upon two species. Bimolecular reaction. Bi means two. So here the rate will depend upon nucleophile as well as the substrate. This is the mechanism. What's happening here is the nucleophile will attack the electron deficient carbon of the substrate and the leaving group will leave. And in between, we will get a transition state. It's a really high energy state. We cannot separate this out of the reaction mixture or anything. Here, in this particular case, this bond is getting formed between the upcoming nucleophile and this bond between the carbon and the leaving group, carbon and our halogen, it is getting broken. And this takes place, the bond formation and bond breaking. Both of these processes occur simultaneously, and such reactions are called concerted reaction, or we can say that substitution nucleophilic bimolecular reaction follows a concerted mechanism. And then this bond will get broken completely, and we will get our product where the nucleophile has replaced the halide ion. So this reaction is a single step reaction. So substitution nucleophilic bimolecular reaction is a bimolecular process which follows a concerted mechanism, which follows a single step concerted mechanism. Here there's another depiction of this reaction given. Okay. The incoming nucleophile interacts with alkyl halide, causing the carbon halide bond to break, and a new bond is formed between carbon and the attacking nucleophile. It's a concerted mechanism. The configuration of the carbon atom under attack inverts in such a way that in much the same way as an umbrella is turned inside out when caught in a strong wind. This process is called inversion of configuration. So first, let's see what a configuration is. Configuration means the spatial arrangement of functional groups around the carbon is called its configuration. So this is a carbon, and how these groups, we know that carbon has 4 valency, and how these groups are arranged around the carbon atom. It is called its configuration. Okay. So in this reaction, what's happening is there's an inversion of configuration. We'll see what inversion of configuration is in the upcoming slide. So In summary, SN2 reaction is a single step reaction. Its rate depends both on substrate and nucleophile. It has a molecularity of 2. It has an order of 2. Then I said that there's an inversion of configuration. This inversion is called Walden inversion. It's another name. Walden is the scientist who studied these reactions. So nucleophile attacks from the backside of the leading group. We'll see that in detail in the upcoming slides. Now let's see about order of the reactivity. Always the primary halide will react faster in case of SN2 reaction than secondary halide, which in turn is reacts more faster than tertiary halide. Let's see why. So in the last slide, we said that the nucleophile attacks from the backside. So this is a methyl halide. Here, the nucleophile can approach the electron deficient carbon really easily because there are only hydrogens attached to this carbon and there isn't much steric hindrance experienced by this nucleophile. So this is a primary primary halide. So the nucleophile experience a bigger steric hindrance when compared to methyl halide. So when we come to the secondary halide, isopropyl secondary halide, there is even greater percentage of what steric hindrance experienced by this nucleus. So this electron deficient carbon is not much accessible to this nucleophile now. And in the case of tertiary, there is a huge bulk around the carbon. So it's really, really hard for this nucleophile to attack this carbon. So here the relative rate of the SN2 reaction is given in the parenthesis. So here the relative rate is 30. Here it is 1. And in the case of secondary, it's 0.02. And we can see that in the case of tertiary butyl, it's 0. See how much difference is there from methyl to tertiary butyl. The reaction is really, really hard. It doesn't happen in the case of tertiary butyl halide SN2 reaction cannot happen. Okay. Then the second mechanism by which nucleophilic substitution reaction can happen is substitution nucleophilic unimolecular reaction, that is SN1 reaction. Okay, this species 2-bromo 2-methylpropane. What is this? CH3, C, CH3, CH3. Yeah, this is 2-bromo 2-methylpropane is the condensed formula written here. This reacts with the nucleophile, and what happens is we are getting a product in which this Br group is getting substituted with OH. We are getting an alcohol. In the last slide, we saw that a tertiary alkyl halide doesn't undergo SN2 reaction as there is a lot of bulk around the carbon atom and there's a lot of steric effects and all. So let's see how it's possible to replace this Br with this OH minus group. So this mechanism, SN1 mechanism, substitution nucleophilic unimolecular reaction, occurs in a two-step mechanism. Okay, in the first step, the alkyl halide, the carbon and Br bond, carbon and halogen bond gets broken and we are getting a carbocation. Carbocation and Br minus. So in the first step, the CBr bond is getting broken. This is a reversible reaction and this is the rate determining step. Rate determining step. What's the rate determining step? It means that this is the slowest step of this two-step mechanism, and the slowest step always determines the rate of a reaction. Why is that? Let's see a real life example. So let's say it's just a hypothetical case. Uh, don't think too much into the numbers and all. Let's see that there's a car company, a car company. So there are three units which makes up this car company, and the first unit makes the body of the car, and second unit makes the okay, this makes the body of the car, and this makes the engine and stuff, other stuffs, and the third unit does the painting. Let's just say this example is just for you to understand uh, why the slower step becomes the rate determining step. So let's say that the body making part of this company has capacity of making 30 car bodies in a day, and engine making part has the capacity to make 20 engines a day. But the painting, it takes a bit more time. Painting takes more time and it's a slow process, let's say. And you can do painting of only 10 cars in a day, suppose. So in a day, even if you run the first two parts to the maximum capacity, we will only be able to produce 10 cars in a day, because the painting, which is the slowest step of this process, takes that much time, and only 10 cars will get completed in this process. So in a similar way, whichever step is the slowest step will become the rate determining step, no matter how fast the second step is happening. If the first step is slow, that is the rate determining step. So in the rate determining step, only one molecule is involved. That is why this reaction is called substitution nucleophilic unimolecular. Okay, so there is a formation of carbocation, and after that the the nucleophile comes and attacks this carbocation in the second step, and we'll be getting our product. So this reaction is very much dependent on the stability of the carbocation, and we know that tertiary carbocation is more stable than secondary carbocation, which is again in turn more stable than primary carbocation. That's why tertiary carbocations prefer to undergo unimolecular reactions. Okay, so order of reactivity of alkyl halides towards SN1 and SN2 reaction. This is whole thing is summarized here. So tertiary halide undergoes reaction via SN1 mechanism, and we can see that methyl and primary halides undergoes reaction prominently via SN2 mechanism. In this case as well, if we take an allyl halide or a benzyl halide, in these two cases, if we are getting a carbocation of this side with this sort, allyl carbocation and benzyl carbocation, these two have extra stability. So if we are reacting a allyl halide or benzyl halide, and we are subjecting it into a substitution reaction, these two will follow SN1 mechanism, in which there's a formation of carbocation is involved. This is all with respect to alkyl group, and if we consider the halide part of the substrate of the RX part, in both cases, in SN1 as well as SN2, the same order is followed, where Ri is more reactive than Rbr, which is again more reactive than RCl, which is much more faster than reactive than RF molecule. We know that iodide ion is a really big molecule, so the carbon iodide bond will be, the bond length will be more. So more the bond length, the weaker the bond will be. So it will be easier to break the Ci bond, which is easier than CBr bond. And to break the CCl bond will need a little bit more energy, and RF bond, CF bond is much more stabler than CCl bond, which is why the reactivity of RF is really less. Okay, let's see some examples. In the following pairs of, okay, I cannot see the question properly. Okay, in the following pairs of halogen compounds, which would undergo SN2 reaction faster? So here two pairs are given, and let's see which one of them will undergo which SN2 reaction. So SN2 is the mechanism which takes place in a single step. There's only formation of transition state. So whichever molecule is less hindered, in whichever molecule there is less steric hindrance, that will react faster in the case of SN2. So here, this is a primary carbocation, while this is a secondary carbocation. We know that primary carbocation reacts faster in the case of SN2 reaction. So this one will faster. This one will undergo SN2 reaction. And in this case, first one is Ri and the second one is RCl. We just saw that it is easier to break Ci bond, and Ri will undergo reaction faster. So this one will undergo SN2 reaction faster. Whether this is about SN1 or SN2, this one will be more reactive. Then the next question is, predict the order of reactivity of the following compounds in SN1 and SN2 reaction. The four isomeric bromobutanes. Which are the four isomeric bromobutanes? First one would be 1, 2, 3, 4. This one. Then this one. Then we have, wait, this one. Then 1, 2, 3, 4. Okay. So this one is a primary compound. This is a secondary compound. This is a tertiary compound. This again is a secondary compound. So let's see how fast they react in the case of SN1. In SN1, there's a formation of carbocation. So whichever one forms greater a carbocation having greater stability will react faster. Let's number these as 1, 2, 3, and 4. So if you are talking about SN1 reaction, we know that tertiary carbocation is much more stable. So the third molecule will react faster. Then we have two secondary molecules, and of these two, this fourth one will react faster, and then the second one, and then the first one, which is primary in nature. And if you are talking about SN2 reaction, the order will be just the opposite. For SN2, the order will be 1 greater than 2 greater than 4, which is again greater than 3. Okay. Then next, let's talk about stereochemical aspects of nucleophilic substitution reaction. Stereochemistry deals with spatial arrangement of the molecules around the central atom, how these groups are arranged in space, and all those things are studied in stereochemistry. So to know more about that, we need to know certain terms, and let's see some basic concepts of stereochemistry. So optical activity. What is optical activity? The plane of plane polarized light produced by passing ordinary light through nickel prism is rotated when it is passed through the solutions of certain compounds. Such compounds are called optically active compounds. Okay, what was that? That sounds so complex, but the concept is actually quite simple. So let's see. This is our this is a light source, and this is our normal light, where there is vibration in all directions, and we pass it through a polarizing filter. Okay, we pass it through a polarizing filter. In this case, it's this nickel prism. Nickel prism is the polarizing filter, and this will turn this normal light into a plane polarized light in which there is vibration in only one plane. Okay, this is our plane polarized light. Plane polarized light produced by passing ordinary light. So ordinary light is passed through a nickel prism, and we got a plane polarized light. And the plane of plane polarized, this is the plane of plane polarized light. And when we pass this plane polarized light through a chiral compound or a sample, a solution of a sample, the plane will get rotated by a certain angle. Okay, the samples or the compounds which can rotate this plane to a certain degree is called optically active compounds, and this phenomenon, this ability to rotate the plane of plane polarized light is called optical activity. Okay, the angle by which the plane polarized light is rotated is measured by an instrument called polarimeter. We can use polarimeter to measure the angle by which the plane polarized light is rotated. If the compound rotates the plane of the light to the right, that is, if the light is getting turned in the clockwise direction, then it is called dextro-rotatory. It's denoted by D form or with a plus sign. If the light is rotated towards left, that is anti-clockwise direction, the compound is said to be levorotatory. In short, it's written as L form or just a minus sign. This is completely an experimental result, and we have later, while you study more in stereochemistry, you will come across capital D and capital L. These two are about configuration. Here, this small letter D and L, these are about optical activity. This is a experimental result. We can only see whether the compound is dextrorotatory or levorotatory by doing experiments, and this D and L are completely different. It talks about configuration of that molecule. Okay, so the plus and minus isomers of the compound are called optical isomers, and the phenomenon is termed as optical isomerism. Okay, now let's talk about molecular symmetry, chirality, and enantiomers. If all the substituents attached to a carbon are different, the mirror image of the molecule is not superimposed on the molecule. Such a carbon is called asymmetric carbon. So we know that a carbon has a valency of 4. If all four groups that are attached to this carbon are different, then its mirror image cannot be superimposed. What do you mean by superimposing? Superimposing means when we place one thing over the other, or it will not overlap, or it will not sit perfectly over the first one. That is what non-superimposable means. Okay, so a carbon in which all four groups are different, its mirror images will not superimpose with each other. So such a carbon is called asymmetric carbon or a stereocenter. The asymmetry and non-superimpossibility of it's superimpossible, not superimpossible. So some people take it mistakenly say superimpossible. So it's not superimpossible, it's superimpossible of mirror images is responsible for the optical activity in organic compounds. So optical activity, we learned what optical activity is. The optical activity uh, arises from this asymmetry and non-superimpossibility. Okay, the objects which are non-superimpossible on their mirror images, like pair of hands. If we take our hands, they are not superimpossible, not like this. If we put it like this, it's superimpossible. But if we place our hands like this and move our hand in the same plane, it will not superimpose over one another. My thumb of the lower hand comes here, and for this hand, the thumb is here. It is not superimpossible. So we can say that they are what? No, they are said to be chiral. Such molecules are said to be chiral, and this property is called chirality. Here, our hands and feet are given as an example of chirality. And take this for example, this cup and this ball, whatever object these are. These can be placed perfectly above one another, and they'll be superimposable. So these are non-chiral objects, and these are chiral objects. So here we are given with an example here. So propane 2-ol is taken. It's a mirror image. If you are reflecting it by placing a mirror here, the OH group will come first, then this CH3 group will go to this side, and this CH3 group will come here, and this hydrogen will come here, and we'll rotate it by 180 degree. So when we rotate it by 180 degree, this OH will come this side, this CH3 will go to the back side, and this CH3 will come to front side, and this hydrogen will stay here. And if we try to place this over the first one, these two, after rotation, these two molecules are same, this one and this one, these two are same. So we try to superimpose this one over this one, and these two will superimpose over one another perfectly. So this is a non-chiral molecule. And this one, the rotated mirror image, in which this is our initial molecule D. This one is reflected, and OH group comes first, and this methyl group is this ethyl group is this, and this hydrogen is here. And we rotate it by 180 degree. And what happens is this OH, this molecule is rotated like this. That's how the 180 degree rotation is done. Then this hydroxyl group will go here. This ethyl group will go to backside, and this methyl group will come forward, and this hydrogen will stay on the plane. And if we try to superimpose this over this one, we cannot superimpose them, because here on the wedge line, on the dashed line, we've got a methyl group, but here on the dashed line, we have ethyl group. And on the wedge, we have an ethyl group in the D first structure, and here we have a methyl group. So it will not sit perfectly over one another. So this molecule, the second molecule, butane 2-ol, is an example of chiral molecule. I hope it is clear. The stereoisomers which are non-superimposable mirror images are called enantiomers. Okay, so non-superimposable mirror images are called enantiomers. These form D and F are called enantiomers. They possess identical physical properties, namely melting point, boiling point, refractive index. All of these physical properties would be identical, but they only differ with respect to the rotation of plane polarized light. So here the mirror images of lactic acid is given, and as we can see, these two are non-superimposable, and first one is a minus lactic acid and the second one is a plus lactic acid. It's levorotatory and this one is dextrorotatory. So enantiomers differ in the direction in which the rotation of the plane polarized light is done. They rotate the negative lactic acid rotate the plane polarized light towards the left side, and plus lactic acid rotate the plane polarized light towards the right side within the same magnitude. Okay, a mixture containing two enantiomers in equal proportions will have zero optical rotation. Why? As the rotation due to one isomer will be cancelled by the rotation due to other isomer. I told you that enantiomer, one of the enantiomer will turn the plane polarized light towards right and the other one will turn the plane polarized light towards right side. So what happens is these two effects get cancelled with each other, and in net effect we will observe a zero optical rotation. So such a mixture is known as a racemic mixture or racemic modification. It's denoted with a DL or a plus minus sign within a parenthesis. The process of conversion of an enantiomer into a racemic mixture is known as racemization. So when an enantiomer is converted into a racemic mixture, the process is called racemization. Okay, we have a question here. Identify chiral and achiral molecule in each of the following pair of compounds. So let's see all these compounds. In the first one, here we have a asymmetric carbon or a stereo center or a chiral carbon. Here one group is hydrogen, another group is OH, then Br, then it's a methyl group. All four groups are different, so this is a chiral molecule. But here two groups are same, two bromine are attached to the same carbon, so this one is not a chiral. And in this case, if we consider this carbon, this group is different. This is a methyl group. Here we have an OH group and then a hydrogen. All four groups are different, so this is a chiral molecule. But here we have H and OH. These two are different, but this group and this group are the same. So this molecule is not chiral. And in this example, what happens is this molecule is chiral because this carbon is chiral, where one group attached is this hydrogen, second group is this ethyl group, then this bromine, then this methyl group. So all four groups are different. So this is a chiral molecule. But in this case, there is no carbon in which all four groups are different. So this is a achiral molecule. Then the last concept is retention. The preservation of the spatial arrangement of bonds to an asymmetric center during a chemical reaction or transformation is called retention. If the configuration doesn't change after a reaction, then we can say that the reaction occurs by retention of configuration. Okay, if no bond to the stereo center is broken, the product will have the same general configuration. Here, see, okay. This carbon is our stereo center, and the bond is getting broken from this carbon and or hydroxyl group. So there is no bond is broken or new bond is not formed at the stereo center. So the configuration does not change. The configuration get retained. See, here an interesting fact is that the rotation here it was levorotatory, but the product is dextrorotatory, but the configuration has not changed. So the configuration and the rotation, direction of rotation would be different, and those two are not related with each other. Okay. Here we have another example, and here of this molecule, the X group is getting substituted by a group called Y. So by A, we can see that all groups are facing the right side. In the product as well, all groups are facing the right side, and new group is attached at the same position as the X. The Y is attached at the same position as X. So there is a retention of configuration when A is formed. And in the case of B, these groups are now facing towards left side, and the Y, the new group, has attached at the back side of this compound. So here there is a inversion of configuration. Here inversion is there. Here it's retention of configuration. So if you are getting an equimolar mixture of A and B, then we can say that there is racemization happening. So that's what all three concepts are. Now let's have a fresh look at SN1 and SN2 mechanisms by taking examples of optically active alkyl halides. Till now we have discussed all optically inactive alkyl halides, and now we are taking an example of optically active alkyl halide. So in the case of SN2 mechanism, there is an inversion of configuration. Inversion of configuration. See, here all the bulky groups are facing towards left side, and the nucleophile is attacking from the back side, and what happens is the configuration gets inverted as a umbrella turning upside down, and now the new nucleophile is attached at the back side of the initial configuration. So we are getting this type of product where there is a inversion of configuration. So in SN2 reaction, there is a complete inversion of configuration. And in the case of SN1, there is a racemization happening. How is it? How does it proceeds to be a racemic mixture in the product? Let's see. So in the first step, a carbocation is formed, and this carbocation is a planar structure. This carbocation has planar structure, and there is this vacant p orbital here. Here we can see there is a vacant p orbital, and the new nucleophile can attack either from the upside direction or from the downward direction, as the all groups, this ethyl group, methyl group, and hydrogen, all these groups occupy the same plane. So the incoming nucleophile can attack either from the upside direction or from the downward direction. So there is an equal probability by which the nucleophile can attack from either sides. So we will end up with a dextrorotatory product and levorotatory product. This is in nutshell what mechanism of SN1 and SN2 reactions look like. Okay, thank you.